In power transmission systems, a bottleneck refers to a situation where a specific component or section of the network has limited capacity to carry electrical power, constraining the overall transmission capacity of the system. This can prevent the efficient flow of electricity from power generation plants to consumers, causing inefficiencies, congestion, and even the risk of system instability or blackouts. Bottlenecks can occur due to physical limitations in transmission lines, transformers, substations, or control systems. Transmission bottlenecks in power systems are a multifaceted issue, driven by growing demand, the rise of renewable energy, and aging infrastructure. Causes of bottlenecks in power transmission: inadequate transmission capacity. When the demand for power exceeds the capacity of transmission lines, the lines may become overloaded, leading to congestion. Old or aging infrastructure. Transmission systems with outdated or aging infrastructure may not be able to handle increased demand, especially as the grid evolves to integrate more renewable energy sources. Geographical constraints. In some cases, geographical challenges make it difficult to build additional transmission lines, especially across long distances or in areas with difficult terrain. Uneven power distribution. Some regions might produce more power than others, e.g., areas rich in wind or solar resources, but the transmission infrastructure may not be adequate to carry this power to where it is needed most. Intermittent renewable energy. The rise in renewable energy sources, such as wind and solar, has introduced new challenges. These energy sources can generate large amounts of power in specific regions, but the transmission infrastructure may not be able to handle these surges effectively. Impacts of transmission bottlenecks. Increased congestion costs. When bottlenecks occur, system operators may need to rely on more expensive power generation resources that are closer to consumers, raising the overall cost of electricity. Curtailment of renewable energy. If a transmission line is unable to carry the amount of power generated, renewable energy sources such as wind farms may need to curtail their production. Decreased reliability. Bottlenecks can lead to voltage instability, higher losses, and a higher likelihood of system outages. Energy imbalance. If certain areas cannot receive the necessary power, there can be disparities in energy supply between different regions. Techniques to solve bottlenecks in power transmission. Grid expansion. The most straightforward way to eliminate bottlenecks is to build new transmission lines to increase capacity. However, this solution requires significant capital investment and time due to planning, regulatory approvals, and land acquisition challenges. Take an example: the European Union's push for interconnection between member states through cross-border transmission lines to avoid bottlenecks and optimize renewable energy distribution. Upgrading existing transmission lines. High-temperature low-sag HTLS conductors. Upgrading lines with conductors that can carry more current without sagging allows for increased capacity without constructing new lines. Dynamic line rating (DLR). Installing sensors that measure real-time conditions such as temperature, wind speed, and line sag allows operators to use the maximum safe capacity of transmission lines. This helps in utilizing available capacity more efficiently under favorable conditions. Example: in the United States, DLR technology has been deployed in some areas to optimize transmission line capacity based on real-time environmental data. Flexible AC transmission systems (FACS) devices, such as static VAR compensators (SVCs) and thyristor-controlled series capacitors (TCSCs), are used to improve power flow in congested networks. They enhance voltage stability, increase transfer capacity, and reduce transmission losses. Example: in India, FACS devices have been installed in areas of high congestion to enhance grid stability and transmission efficiency, especially during peak load conditions. High-voltage direct current HVDC transmission. HVDC lines are more efficient for long-distance transmission and can bypass AC grid bottlenecks by directly transmitting power over longer distances. HVDC technology is especially useful for connecting offshore wind farms or remote generation sites to the main grid. Example: the NordLink project, connecting Germany and Norway, uses HVDC technology to facilitate the exchange of renewable energy, helping alleviate transmission bottlenecks in the region. Energy storage systems. Using battery energy storage systems (BESS) or pumped hydro storage can alleviate bottlenecks by storing excess electricity during periods of low demand and releasing it during peak demand. This reduces the strain on transmission lines and smooths out the flow of electricity. Example: in California, large-scale battery storage systems have been implemented to manage the fluctuations in renewable energy generation and reduce transmission bottlenecks.
Demand-side management (DSM) involves shifting or reducing consumer demand during peak hours to ease congestion on transmission lines. This can be achieved through time-of-use pricing, incentivizing consumers to use electricity during off-peak hours. Example, demand response programs in the U.S. encourage industrial users to reduce their energy consumption during peak periods, helping to alleviate congestion on transmission lines. Smart grid technology uses digital communication technologies to monitor and control power flows in real time. This allows for better management of bottlenecks by rerouting power or adjusting demand in response to system constraints. Example, smart grid initiatives in countries like South Korea and Germany have improved grid flexibility, allowing for better congestion management and reducing the impact of bottlenecks. Decentralized energy generation. Another approach is to reduce dependence on long-distance transmission by encouraging localized power generation through microgrids or distributed energy resources like rooftop solar or small-scale wind turbines. Example, in Germany, the integration of local solar and wind energy resources into the grid reduces the need for long-distance transmission, alleviating bottlenecks in specific areas. Real-life examples of transmission bottlenecks. Texas, USA. In Texas, the Electric Reliability Council of Texas ERCOT has faced significant transmission bottlenecks, particularly in West Texas, where large amounts of wind power are generated. Due to limited transmission capacity, the power generated cannot always reach demand centers in eastern Texas. This leads to curtailment of wind power and higher electricity prices in areas with limited access. Solution: Texas has invested in CREZ competitive renewable energy zones to build transmission lines that connect wind-rich regions to load centers. Germany, with its high reliance on renewable energy, Germany has faced transmission bottlenecks when trying to transport wind power from the north to industrial centers in the south. The existing grid has been inadequate for handling the large-scale renewable integration. Solution: the country is expanding its grid infrastructure and using HVDC lines to transmit power efficiently across long distances. They are also incorporating energy storage to mitigate congestion during high wind periods. China faces bottlenecks between the renewable energy-rich western provinces and the energy-hungry eastern provinces. The long distance between these regions creates challenges for transmitting electricity efficiently. Solution: China has invested heavily in ultra-high voltage UHV transmission lines, both AC and DC, to handle the large power transfers and reduce bottlenecks between the generation and demand centers. Transmission bottlenecks are a major challenge for modern power systems, especially as renewable energy sources become more prominent. Solutions to these bottlenecks include grid expansion, upgrades to existing infrastructure, advanced technologies like FACTS and HVDC, and demand-side management. Each of these solutions can help ensure the efficient flow of electricity, reduce congestion, and maintain system reliability. In the long term, a combination of these strategies will be necessary to overcome the increasing complexity of the power grid. Root causes of transmission bottlenecks: high power demand growth. In regions where electricity demand is growing rapidly due to urbanization, industrialization, or electrification of transportation, transmission networks may not be equipped to handle increased loads. This mismatch between generation capacity and transmission infrastructure creates congestion. Example, India's northern grid faces bottlenecks due to high industrial demand growth in states like Uttar Pradesh and Haryana, outpacing the capacity of existing transmission lines. Intermittency of renewable energy, particularly solar and wind, are inherently variable. They may produce significant amounts of electricity during certain periods, e.g., windy days, sunny afternoons, but this can lead to localized congestion if transmission lines are not equipped to handle the surges. Example, California has experienced this intermittency problem with solar power, especially during the duck curve effect, when solar generation drops off in the evening, increasing grid strain as conventional generators ramp up. Economic and regulatory challenges. Cost of new transmission infrastructure. Building new transmission lines is capital intensive and can take years to complete. In many cases, the cost is passed on to consumers through higher electricity tariffs, which can create resistance from both regulators and the public. As a result, utilities may prioritize short-term fixes rather than long-term investments in grid expansion. Permitting and siting delays. Regulatory approval for new transmission lines can take years, particularly if lines cross state or national boundaries.
Environmental concerns, public opposition, and land acquisition issues can also slow the process. This delay in grid expansion exacerbates bottlenecks. Example, cross-border transmission lines between the US and Canada face lengthy approval processes from both national and local governments. Curtailment policies. When bottlenecks occur, system operators may curtail the output of renewable generators to prevent overloading the transmission network. However, curtailment reduces the financial viability of renewable energy projects and undermines efforts to decarbonize the grid. Example, in Germany, wind power curtailment due to transmission bottlenecks has led to lost revenues for wind farm operators, resulting in calls for faster grid expansion. Market mechanisms and congestion pricing. In some electricity markets, congestion pricing or locational marginal pricing (LMP) is used to reflect the cost of transmission bottlenecks. These mechanisms incentivize generators and consumers to locate in areas where transmission is less constrained, helping to alleviate congestion. Example, PJM interconnection in the US uses LMP to manage congestion and direct investment toward areas where new generation or demand-side resources can ease bottlenecks.